in the first video on this topic on electricity, I talked about current as being the rate of flow of charge. Well, we're going to talk a little bit more about that. And we're going to talk about the rate at which those charges actually move along the wires. And that's what we call drift velocity. So that's what we're going to talk about today. So in that first video, I gave you the equation Q equals IT. Now, we can actually do better than that. This says that the current is the measure of the amount of charge moving per second. So let's think about this. What is it that the current is actually depending on? Well, it depends on the speed with which the particles are moving. It depends on the charge that they're each carrying. And it also depends on the number of charged particles that are moving. All three of those things are going to affect the amount of current, but none of them are represented in this equation. So if we think a little bit more on this idea, then we can get to a better equation. So if I want to think about how many charge carriers there are, well, what I first need to do is think, well, how many are there per meter cubed? So what we do is we take the cross-sectional area of the wire and we multiply that by the number of charge carriers per meter cubed. And that will give me the number of charge carriers I have in each meter length of wire. I then need to think, well, how fast are they going? So I need to add in the speed of those charge carriers. So let's call that V. So if I want to get the number of charge carriers passing a point in the wire per second, I now have ANV. But we also said I need to think about the amount of charge each of my charge carriers have, so let's call that Q. So the amount of charge passing along the wire per second is going to be ANQV. Now, if I'm just thinking about electric current in a wire, instead of Q, I can use E for the charge on an electron. And I get a new equation where I equals ANEV. So cross-sectional area times the number of electrons per meter cubed times the charge on an electron times what we call the drift velocity, so the velocity at which the electrons move from one end of the wire to the other. Now, just a little note, the number of electrons per meter cubed, that's sometimes also referred to as the electron number density. So if you see that term, it's just the N. So now that we've got this equation, let's just have a go at doing a quick question real fast. So all I want to do is calculate the drift velocity of electrons in a copper wire, cross-sectional area 5 times 10 to the minus 6 meters squared, when the current's 1 amp and the electron number density is 8.5 times 10 to the 28 meters per meter cubed. Have a little look at your number, make a comment on it. Do this if you've not done drift velocity before, and really have a think about what your number is. So I suggest pausing and doing that. I'm going to go to the answer now though. So what we need that to do then is I equals ANEV rearranged to V equals I over ANE gives me 1 over 5 times 10 to the minus 6 times 8.5 times 10 to the 28 times 1.6 times 10 to the minus 19, which gives me a drift velocity of 1.47 times 10 to the minus 5 meters per second. Comment: this is very slow. I hope that's your first feeling when you see this. My word, that's slow. And what you have to remember though is that this is a velocity. So we're talking about the rate at which they are moving from one end to the other end of the wire. Not how fast they're actually moving. This isn't their speed. This is the rate at which they're moving along the wire. So the electrons do actually move a lot faster, but they travel from one end of the wire slowly. So the way to think about it is they're not travelling in straight lines. They bounce around all over the place and they collide with the ions in the wire, so the positive ions that are vibrating in the wire, they crash into them. So we often think about it as being the average speed as they travel along the wire, and that's your drift velocity. So there are things we can do to our wire that can affect our drift velocity. So we've got a couple situations here. So without telling you anything else about the wire, but I can say I've got a wire, it's the same material, but I'm going to double the current through it. How will that affect the velocity? So in this instance, I've got double the normal current. So that means I'm going to end up with double the velocity. Because if we think about our equation, I've got I equals A, N, E, V. I'm saying that A, N, and E stay the same, so they're a constant. So that means that I is proportional to V. So if I double I must double V. Okay, so let's have a look at another one. So this time, same material, same current, but this time I'm going to change the cross-sectional area. So I'm going to half the area. What does that do to the velocity? So I need to think how are V and A related to each other. So I had I equals A, N, E, V. So V equals I over A, N, E. So I, E, and N are constant. So V is proportional to 1 over A. So if I half A, I'm going to double the velocity. So I'll be looking for the inverse proportional relationship there. And last thing I could change then, so I'm going to have same current, same size wire, but I've got a different N density. So I've got a different number of electrons per meter cubed. So what I'm going to say is I'm going to half the electron number density. What's that going to do to my velocity? Well, if we think back to the rearrangement we had for A, I have that I over A, N, E equals V. So N was on the bottom, everything else stays the same, so V is inversely proportional to N. So if I half N, I'm going to double V. If I double N, I'm going to half V. Looking for these proportional relationships is something you need to get used to because there are lots and lots of questions that are all about proportionality. So you can normally spot a question about proportionality because they won't give you all the numbers you feel like you need. They might just tell you that in situation A, this is the current and this is the speed. In situation B, I've kept everything the same, but here's your new current. What's the new speed? So you then look for what's the ratio by which the currents have changed, what's the relationship between current and velocity, so therefore how's the velocity changed? Practice is the thing to go for with those. Right, I got a little sidetracked there, but those are important things to think about. Real fast, couple last little things on this. So conductivity. Good conductors have loads of free to move electrons, so they have a high n value. Insulators don't have many, so small n value. And the last thing we need to know about are semiconductors. So semiconductors are things that when the temperature increases, more charge carriers are released. So in a semiconductor, the n value can change when we change temperature, which therefore changes whether or not it can conduct or not. Okay, that is it. So hopefully you now feel that you've got a better equation than Q equals IT. And you've now got I equals ANEV. They're useful for different things, depends what detail it is that you're looking for. Okay, so that is it. If you want a challenge to help you become a better physicist, what I suggest you do is you take the equation I equals Q over T and I equals ANEV and show that the units of both those equations are definitely the same. It would be good for you practicing with your units and you're looking at base units and things. It would be really good practice to go through. Okay, so remember, any questions? Ask me this evening.